Okay, so the first section of today's discussion is what I call the crash course in the nuclear chemistry. I did it for the previous session, but I don't mind to doing again because I only made two nuclear chemistry crash course, and this is the first version, which is an emphasize the basics of the nuclear chemistry, and also show you the what I call the valley. What do you call the valley of stability? Okay, so this is something that we want to discuss. So let's zoom it in to this experiment by the Rutherford. So Rutherford did an experiment. At that time, they didn't know actually even what electron was. So they only knew that there is they can generate some ray of something, a particle. You can shoot it through. And then the Rutherford experiment, he essentially applied the electric field. So this is a positive terminal, this is a negative terminal. And you can do it using your the galvanic cell, voltaic cell. So you can generate using the battery. You can put the positive terminal there, negative terminal there. And he find out some particle actually being attracted to the positive side, right? So this is what is called, this must be the positively charged particle, right? And he also called this is an alpha particle, okay? And it just name comes from the first one is an alpha. The second one was a beta, which is the opposite, this being attracted to the positive terminal, and this is called a beta. And later he find out alpha particle was nothing but helium with atomic number 2, atomic mass 4, it's no electron. So that's the helium particle, alpha ray, and people also use this notation as simple as that because they know it's a positive particle, but also this one is so unstable. If you expose it outside, they will get the electron from somewhere else. If there is available, then they can be just being neutralized, so that they can be happy. So anyway, that's an alpha, and the beta particle is nothing but electron with almost no mass, and charge is opposite to the proton. And at that time, they didn't have what an electron was, so they just say, first one is alpha, second one is beta, so that's why it got the name. And the third one, it just went straight through. Do you remember this is very similar to the diamagnetic. If you have a diamagnetic particle under the magnetic field, they just go through it. This one too, gamma ray just go through it. That means it has no charges. It is actually just a photon with an energy in a form of an h nu, right? H, I think it's a lambda over c, right? So, c over lambda, meter per second. Yeah, I think the c over lambda. Okay, anyway, let's just say that this is just an electromagnetic field, and the light that just propagating through like this, and so it has no charges. So they just say alpha, beta, gamma, and you just need to know. And there's a nuclear symbol that you got to get familiar in the nuclear chemistry. This is the one I kind of find it in your slide note, and this is to me the most important one. And certainly the proton, neutron, and electrons are one that we kind of saw it a lot. And to me the most important one is for you to understand is this numbers is sort of related to number of protons, right? And then the other numbers is related to the total mass. So electron considered to have almost no mass, whereas a neutron and proton has about the same mass, and so they have these notations. And then we all know we have covered that the alpha ray is helium, so is atomic mass 2. Beta is electron, so it's the same as an electron. And the positron is somewhat like opposite charge. It's like an electron, but it has opposite charges. So it's like an antimatter in a way. They call it antimatter, which is an opposite side of the matter. when the electrons and positrons meet each other, and actually they disappeared, and then energy is liberated, and that's what is going to happen today. I have a good attendance today. Last week I only have a fraction of this. Today we have 25 people joining. I'm very happy, and please make sure do your best to attend this session as much as I can. Thank you very much. Okay, so let's see, where am I? All right, so this alpha, when you say alpha, that's really the helium, okay? And like I said, also remember helium has a +2 charges, total mass 4, atomic number 2. So that's actually positively charged alpha particle. Beta is, people just use a beta. Also, sometimes they use a beta minus, just to make sure that they are doing this. And positron is they are using the beta plus. And they hardly use the beta as it is, because beta is intrinsically assumed that it is an electron. Okay. So this is an example of where the different types of reactions, and then there is one type is an emission, the other one is a capture. Okay, so emission reaction can be viewed something after reaction is being emitted, right? So this is being emitted, and what is being emitted? Beta is being emitted, and that means electron. Positron is being emitted. That's what it is. So so you can either people write this, but more commonly people write this. That's an electron emission. That's a positron emission with +1 and 0. Okay, and as you can see, this number of proton matches, and the total mass is matching, and so the numbers up and numbers downs are always matching each other, and that's the way it is. And the capture has a different perspective. So capture means for the reaction to occur, electron is needed, right? So that's an idea about what is called a capture. And this capture is shown here. For example, the proton and the electron capture will result in the number of protons are going down. So this is where you have a decrease in the number of protons while keeping the mass of everything the same, right? So that's what it is. So if you notice here, for the beta emission, you will see that the neutron is now changed into the proton. So number of proton is increasing for the beta emission case, whereas I guess nobody says a beta capture, but it's a electron capture, which is an opposite reaction that you guys see on here. And I am showing you the answers to the first problem in the discussion. And if you go back and looking at my first discussion problem answers, you will see the details. And actually, I provide the background as well. And then to me, the most important one that you should pay attention to it is the following. So when people say 94, that is an equivalent for me to say it is a plutonium. So sometimes they say the plutonium, and you need to look at the periodic table and figure that out. That's a plutonium. And so okay, this is I guess we're alpha ray. And so when you have a 94 protons emitting 2 proton containing species, which is an alpha particle, and then you ended up having 92. So the 92 is a uranium. So this is what you're supposed to see. So let me kind of put out. Let me put out this periodic table from the exam reference sheet is not the best. But if you're looking at here, this is a plutonium, which is a 94, and losing 2 proton, you're going to say 92. Say 92 is same as for you to say U, which is a uranium, and so that's what you're writing here. And then the second step, I'm going to use orange colors. So this one is total number of proton and neutron, and that's the total mass, atomic mass for the alpha ray. and 242 minus 4 is 238. So you can complete this reaction by this way. Okay, so just remember the sequence how this is being done. Okay, magnesium is same as atomic number 12, and if they losing the electron, this number should be 13. Looking up the periodic table, saying okay, that should be on aluminum, and then you finish up the rest the top mass balance equation as well. Okay, so this is the same drill. 14 is same as somebody saying silicon, and they are assuming that positron is being emitted, and then you will hand it up 13, that's aluminum, and then you can do the balance. So those are the three categories where some things are emitted, and this is alpha, this is a beta, this is a beta plus emission, right? And whereas the one that I'm using different color, this is a one actually, this thing happens before. So this is a electron capture, and you will see that easier way to balance it out. First, you need to pay attention to 18 and looking up. Okay, so well, 18, where's my 18? 18 is right there. That's argon. So argon is an 18, and then if you got the electron, that's a -1, so your result is 17, and that is a chlorine in the periodic table, and you finish up the rest, and then you can get that. And this, so now you start to wonder why something is like to do this way, something actually likes to lose the electron. So in these cases, you are actually increasing the number of proton by beta ray emission, and this is the one that you are actually decreasing the number of proton by capturing the electron, right? So some of them actually likes to increase the number of protons, some of them actually likes to decrease the number of protons. Why this is the case, right? So that could be some of the question naturally, and the naive, not naive, the general answer can be found from this, what is called the valley of stability. Okay, so let me turn off the light. The valley of stability is what is being written here, and then what you see. Okay, so let me blow up. This is from your the class, and you see the number of protons here. So that's a G. Okay, and then this is a number of neutrons. So that's N. And then this is a line that shows N equals Z. And N over Z is 1. So what that means is the number of protons and number of neutrons is the same along this red line. And up to 20, okay, 0 to 20, you essentially most abundant atoms in the isotope is essentially same number of neutron and same number of proton. The ratio is 1 to 1. And do you remember, for example, the carbon has atomic number 6, but their atomic mass is 12. So what that means is protons is there are 6 protons and there are 6 neutrons, so same number of neutrons, same number of proton. That is behave really well up to kind of the number, atomic number 20. So let's have a look at it. I think that I have a, this one, yeah, here we go, right? Atomic number 20, so up to here, right? Calcium. So this is a pretty, to me, the well behaving set, from the hydrogen to the carbon, nitrogen, oxygen, silicons, and up to calcium. The other one is a lightweight element, right? Light mass element. And if you go start to up, this is getting more complicated. And then they start to have a generic trend that, okay, what is the ratio between the number of proton, which is simply the number that you see as an atomic mass, that's the number of protons, so that defines what it is. And then what about the number of proton and neutron combined? That's an atomic mass, but let's try to extract the numbers of neutrons out. And once again, this one comes in handy. And then what they find out is the trend is kind of stays here, and then they kind of go up. You see this? They kind of go up, and they stay here. Okay, so this is a valley, and so this one has a two meanings here. Is this here is a one that will be unhappy, right? They are not happy because this is unhappy, happy balance, right? So this is you want to within this valley of the stability. You don't want this is a too little z, or I would say protons, and this is a two. So in this case is from here, you have a two actually. You have a too much. Okay, this is I loaded it a different way. You are unhappy because if you are in here too many protons, right? And this is a too little protons. And so this is also unhappy if you are in this. Okay, so if you are in this. Okay, so if you are in here, so only where you are happy is what I circle here is sort of the red dots here. So, and this one, they're trying to kind of make it categorize. Okay, atomic number 20 to 40, the ratio, neutron is about 25% more. If you go up higher, is even more. It's deviated from the 1-to-1 ratio, is the difference is higher for even higher atoms and something like this. There's no stable nuclei. Any scenario can happen, but it's all over the places, right? But it's a really good, they behave really well up to 20. But the good thing is to know is n over z smaller than 1. This is not good, okay? Not good. They want this number, right? This number to be bigger than the ratio of 1. Okay, so that's one thing that I wanted to explain it to you, and that we can solve this problem. And there is some problem that I can elaborate a little bit for the previous exam. Okay. Okay. Yeah. So this is the next one. Okay. So I got 26. That's next one. So this is actually also I kind of crop out something that from the your class slide, and as a recap, I just say you heard about alpha, beta, gamma, and alpha is nothing but helium particles, right? So heliums, and the beta is just an electron. That's a beta. And the gamma is, they use a symbol like this because it's just a electromagnetic wave, right? So that's electromagnetic wave. And then this is an alpha, which is a helium. That means 2, it's 4. And sometimes they write it 2 plus. Sometimes they just write it the other way. So that's an alpha, that's a beta. And the positron is, we are using, once again, using the beta plus, and so that's the symbol, atomic symbol that people use this way. Electron capture is the one actually happened before the reaction to occur. So this one is actually looking at here. They love to actually decrease the number of protons from 44 to 43, and they change the element from ruthenium to something else. Okay, so that's what happened here. And all the answers can be found here. So you need to really have yourself to get used to it. And obviously, I think the nuclear chemistry was there's an outburst of the nuclear chemistry, understanding it because we lived through the eras of atomic energies. And if you look at here, there's a plutonium is right there, and the uranium is right there, and this is the whole thing that. Understanding about the chemistry related to something that can cause a nuclear reaction is very important. So let me stop here. That's